Okay, I think recording has started. Let's begin with the mortality models concept from the first day. And I'll share these handwritten notes with you, but it's better to go with me and you can create your own um, lecture note as well, depending on the summary, because it's easy to memorize the notation if we all can work together. So let's start with mortality models. And I mentioned, so insurance is always, uh, which means, yeah, let's say like that. In the insurance, we always have to work with some kind of fatal events. So it can be a death of a policyholder, or it can be a damage to a property, and it can be a financial loss of an investment. So there are many different losses that we can face during our investments or during our like this taking risks. So we can take risks in different ways. So it can be a financial risk, it can be a health risk, it can be a life risk. So among these risks, we can select many of them as insurable, and there are some risks that are not insurable. And even for some risks, we can insure that risk up to some point. So that is the concept of sharing the insurance with different insurers, or sharing an amount with the insurer, and the other amount will be taken care by the policyholder. So there are many different combinations of insurance products. So the basic concept to divide these things to two parts are considering the time of the which means the insured period, and the type of the risk. So based on these two, we can divide the insurance models into short-term models and long-term models. So if the business line, or if the investments, or kind of a particular property is considered as a short-term, which means are subjected to a short-term risk, so then we can use a short-term insurance model to model that risk for the particular financial or health-related risk. But if the type of risk is long time dependent and longitudinal, which means it is subjected to a repeated incidents, and also we have to monitor that process for a long time. If the business line is, which means it has a long tail for the risk, that means we can expect many large risk at some point of the timeline. So then we will model those types of risk using long-term insurance models. For both of these methods, we have to consider the incident as a suppose a death, but at some point it is not an actual death. For an example, we can use these models in a production line and consider the time to break down of a production machine. Or we can consider some components of a machine and only consider about those components. It's currently 7:45 p.m. with a likewise, we can apply these things to many different applications. So in this course, we are basically focusing on insurable life risks and health risks. So that is why we are taking care of, which means discuss the methods that are taking care of life insurance mostly, but it can be a health insurance as well. So these types of insurance coming under the long-term actuarial models. So for those things, the mortality models are defined using few probability functions, and you can see these kind of concepts are also used in survival analysis for medical statistics. So there's in this part, we have a combination, which means a connection with medical statistics, because we always use survival functions and um, find the survival probability or the probability to the event. So it's always that if the time is considered, it's a time to event data point. So we can use the same types of survival functions to analyze this. But in actuarial models, the specific, which means we have developed some specific models to fit into different kind of scenarios of insurance, which makes us to use it as a tool so that we don't have to do these calculations from the beginning. If we can define the type of the insurance with respect to some of these guidelines, we can directly fit the model using already defined techniques. So that is why later we use actuarial notations to work with these kind of different risks. So because we need the reproducible models, which means for the same type of processes, we will have different measurements. So using those different measurements of, it can be a time to some fatal disease, or time to retirement, time to death, or it can be a pension plan. So for these kind of different payment methods, we can fit the scenario into a predefined model, so that we can use that model without worrying about definitions and working from the fundamentals from the beginning. So that's why we tend to move to work with actuarial notation later, but still we are using the same concepts in these survival analysis modeling. So let's begin with the probability functions we need to consider in this case. So for probability functions, we have survival function at first. So as I mentioned, we always work with the time measurement, and we know that if it is a life or health insurance, the policyholder buys that product at some point of the lifeline. That means at age X, that person buys the product. Then we have a random variable called Tx, which starts from 0 and goes to somewhere in the future of the point in. So this time point can be considered as the event time. So this event can be a different event, as I mentioned, but if you are taking in terms of life insurance, it can be the death. So in this course, we will mostly using the time to death measurements of a policyholder, assuming that we are always thinking about life insurance policies. So then this is the common framework we will work with in this course. So apart from that, we have a T note as well. So this T note says the time to the event, but it starts from the beginning, which means it starts from the birth in terms of the life insurance. But this can be, if this is related to a machine, so then this is the time that machine is, which means open to the time that machine was open to work. And if it is this, so that means after the production, so it wasn't working for X years, and after X years, the machine was put into the production line to begin work. So that means the same thing after age X, I'm going to buy a life insurance policy from a company, so that if my age is 30, so then this is 30 and my random variable is T30. So from the age of 30, I'll be waiting for the event in future, and I have passed one of my risks to the insurer. That means I am passing, so I'm afraid that I will have to face a financial loss at some point due to a work-related damage, so that I am passing part of that risk to a third party, which is called the insurer, and the company will take that risk on behalf of me, and I have to pay some amount of money for them to taking care of my risk on behalf of me. And as the benefit, they will pay an amount to me at this point if the event occurs within the contract period. So that it's like this. So I'm paying to the company to take some part of my risk and taking care of that. And the company will use my money for some kind of investment, and then they will pay back to me if I face that risk at some point of the contract period, or they can modify the policy to pay some kind of survival benefits at the end of the time period. So that will be the common frame. So to do that, we need to deal with the probability, because always we cannot find the exact time of event, so that we have to consider all possible times of the event. That means we need to have a probability distribution, and that probability distribution provides the survival function with respect to this random variable, which is the time to event random variable starting at X of the timeline. So if my age is X and if the event is at T, so then at that point, my age is X plus T. So that is the basic thing you need to keep in mind when you're working with these models. So let's start with the model definitions now. So the survival function can be denoted using SXT, so which means the survival function starting at age X, and the T is the term that is varying with the time. So this says the probability that X survives to 2 years, or T years. So T is the random part. So I can say the time to death random variable is greater than T. That means we know for sure the time to death is greater than T, and the person has survived up to the time point T. And then if I use the random variable, which is coming from the beginning, or which is coming from the birth, so then the same event can be written like this. The time to the event from the birth is greater than the age X plus T, given that this person has already survived to X years. That is why. So if he is surviving at age X, then he can buy this product and survive for T more years. So that is the same event in here. Then I can write down this using the concept of conditional probability, so that I can write down the joint of these two events using the same survival function. Now this survival function related to the starting time of 0. So this one is related to the starting time of X. And it says a person I think there was a problem in the connection, so I'll share it again. Okay, so what I was describing, that the same survival function can be approximated using the conditional probability concept, where the event is surviving from birth to x plus t years, given that the person has survived for x years from the birth. So that is the basic definition for the survival function related to the time to death variable of a person who purchased an insurance product at age X. So this survival function has some property that at time 0, which means at this point, the survival status is 1, which is almost sure that that person has survived at this time. But when it's go to the maximum lifetime, so it's going to be 0. So it is a non-increasing function of t. That means it's always, so this one is always decreasing with t. So these are the 3 properties of this survival function. And now, using this survival function, and I can recall you that if you know the survival function, so it is same as 1 over the cumulative distribution function, so which is 1 subtracted by the cumulative distribution function of that tx random variable. So in the actuarial notation, now I can use these concepts and define some actuarial notations for these probabilities. First one is the probability, which is, this is the simple P, that a person at age X survives for T years. So that is the order. Probability, that person, this is the current age, or the age that buys, which means that person buy the product and then survives for T more years. So at this point, I'm going to this point. So this is the probability that a person at age X survive for T more years. And in the probability notation with the event related to the random variable, it is given like this. So this is the same definition as the survival function. And that is, you can write down like this. So that's why I'm saying that instead of this, which is in the distribution theory part, we'll use this notation. Both has the same meaning. But this one is preferred because we need to do it, which means use it regularly, and we need to reproduce the results so that if everyone can use one single term for the same probability worldwide, so it's easy to work with which means regardless the language we are using, we can use this notation in any part of the world. So that is the main use of this. So that's why we are using these already defined terms, and we need to get familiar with these things. The next one is the death probability. So instead of P, we will use Q. So the death probability of a person at age X, and the death occurs within next T years. So then we can say the probability that a person at age X dies within the next T years. So in terms of the random variable, we can write down the probability like this. So this is the probability, and this is defined in distribution theory as the cumulative distribution function of that Tx random variable. So instead of this, in distribution theory, we will use this notation. So that is the starting point. And by the definition, in terms of the distribution theory part, we know that the summation, which is in here, the summation of the survival function and the cumulative distribution function at one point will sum up to 1. That means we can say the probability of surviving for T more years and probability of occurring the death in the next t years is equal to 1. So this summation is 1. So that is the most basic thing we need to get to know. And the next one is the deferred probability, so that the death occurs of an age x after u years and within the next t years. So this one says the probability that the person is at age x, so we are using tx, and the person survives for u years, and then death occurs within the next t years. That means it's a condition, which means we have two parts now. So if you say like this, now the death occurs in between u and t. So without worrying about finding this event probability using the distribution theory knowledge, we can use the already defined two functions in here. That means we know this person has to survive for u years. After that, the person has survived for x plus u years and death occurs within the next t years. That means u is in somewhere in here and the death occurs in this interval. So the same probability can be defined in two ways again. Like using the survival probability, we know that a person at age x survive for u is greater than, so which means this person survived for this point, that probability is greater than surviving it for t. That means t is far away from that, and we know that this survival function is a decreasing function, so that the difference between these two probabilities will give the same value. That means surviving for u years and surviving for u plus t years. Or we can use the death probabilities and you can get the difference, and you can see, since this relation, if I substitute these things, then I have this relationship. So this is the point where we define all these type of probabilities in the actuarial notation. Now we can move to current future lifetime. In this case, so in here I said this tx is the time to death and it is a continuous measurement from 0 to t. In the current case, which is the most practical one and familiar one to us, so in that case, we are measuring the future lifetime in discrete measurements, like start from 0 and 1 and 2 if it is annually, and the death can occur in somewhere in here, and then we take the kx, or the current random variable for this death measure, as kx, which is the closest integer value from the left, and then we denote this as the random variable kx, which means the current or the number of complete future years. So this is in terms of years, and the number of future complete years for a person at age x prior to death, and denoted by this. So this notation always says we only take the integer part of the tx. So I can define the probability distribution for this kx using the property of tx. So if this kx is equal to a value, that means we know this person has survived up to this point and death occur within a small time interval. So I can say if this is k, so k is the integer value in here. So the person at age X survive for K years for sure, but after X plus K years, death occurs in the next year. So that is why I leave this place alone, which means if we have 1 in here, which means surviving for 1 more year, we don't indicate it as 1, so we just leave it as it is. So this says a person at age X plus K survives for 1 more, or the death occurs for within the next year. So this says the person at age X survives for K years, and now the person has the age as X plus K, and then the death occurs within the next year. So then using this notation, I can write it down again like this. Surviving for K years and death occurs in the next year. So that is the definition. Then I can use the death occurs within next n years as the collection or the sum of these probabilities. Person at age X, death occurs in the next year, and now the person has, if the person survives the next year, then the death can occur in the second year. So that means the age is now X plus 1 and death occurs in the next year. And if the person survives the second year, then the person has survived 2 years and the death occur within the third year. So likewise, we can develop this up to the person has survived up to n minus 1 years, and then death occurs in the next year. So the summation of these terms can be used to define the death probability of a person at age X, and death occurs within the next n years. So one can write it in the same deferred probability notation, and it will be like this. Person at age X survive for 2 years and death occurs in the next year. And likewise, the person at age X survives for n minus 1 years and death occurs in the next year. So that is the definition of this current future lifetime and its probability. Then we have a life table which contains information about the population in terms of number of survivals at time and number of deaths at time, and with many different function values, which will be discussed in future topics. So this life table, the basic measurements are the number of survivals at time and number of deaths at time. Then we can define the probability functions that we have discussed in the previous part. The probability of a person age X and survival for T more years can be defined using the number of survivals of this population at X plus T time point and number of people who are alive at the time of X. So this LX is the number of survivals of this population. It can be defined for 1,000 number of people in the population from the beginning, or 100,000 or 10,000, depends on the numbers it has and the population they consider. So mostly for the life table, it will be a table defined for at time 0. They consider that there are 100,000 lives, and then after that, it will be a reducing or decreasing content, and we are just reducing the number of deaths at each year and define the number of survivors for the next year. So you know that Lx plus T is less than Lx. So then we have a fractional value for this one, and this is a conditional probability. And then I can define the probability that person Hx, the death occurs within the next t years as the number of people who were at x. And so here, this is the number of deaths for the people who were alive at hx and dead by the time t. So the denominator is same as this one because we need the number of deaths with respect to the number of survivors at the beginning. So number of deaths, as I mentioned, we are progressing through Lx column by subtracting the number of deaths at each year. That means if I subtract these two terms, number of survivors at time x and number of survivors at time x plus t, the difference is the number of deaths in between this time interval, which means from 0 to x to x plus t in real age. So at this point, age is x, and at this point, age is x plus k, same amount. So we can find this using the table if we are working for a particular population. And these life tables are defined for different communities, which means for Sri Lanka, we have a table, or we have a common table to use, or we can prepare our own table for the population in a particular land region, because we know that the time of which means the life expectancy depends on the quality of life in each region. So which means we can define different life tables for the people or the general public in that community, or this life table can be which means can be defined for a particular components of a production, like the cell phones or bulbs or any kind of electronic device, or it can be for animals, for a marine life, or even for other mammals, like that. It depends on the population we consider, and for each population we can have different life tables, but still we can apply these concepts for each population because they are universal equations. So the final thing is I can define the deferred life. That means the person meets at age X and survives for U years and death occurs within the next T years. The probability is equal to the number of deaths occurs between U and T in future life. That means in actual age, the number of deaths occurs in X plus U, and we will count the number of deaths for next T years. And still, we are dividing it by the number of survivors at age X. So this is the number of deaths between X plus U and X plus U plus T. That says we need the number of survivors at age X plus U and the number of survivors at X plus U plus T. So this difference is the number of deaths in between these two real life times. And if it was in the future lifetime, which means Tx, so then the time points are U and T. So which means we are taking the number of deaths in between U and T. So that is how we can define these probabilities using the standard life table or any kind of a specific life table that are given to us to solve some or apply this concept to a specific population. So these are the equations that we can use, define the death probability or survival probability or deferred death probability using the life table. And at some point, you might be asked to calculate. So you will be asked to calculate these probabilities using the life table, or you will be given these probabilities as a function of t, and then you can use that to calculate the actual probability using any kind of distribution that we hypothesize on that function. So those are the two methods we will work on this course. And you might have seen in some examples, we used the life table, and at some point, we were given these probabilities as functions of x and t. Now, the next concept is the force of mortality. And this is this kind of, we can consider it as a rate that you can see for a given time on the real line, x plus t. We can define the force of mortality as the ratio of the probability density function of that random variable, and we know that this person has survived for x years. So this ratio defines the force of mortality. And since we have the distribution of we know the connection between the distribution and the survival functions, so I can write down this density function in terms of the distribution function. That means the distribution function, to get the distribution function, I have to integrate this density function. So if I differentiate the distribution function, I can get the density function. So, and we saw that for the distribution function, we can use in actuarial notation, we can use pxt. And if I differentiate it respect to t, and the negative value of this one is equal to the density function. So, and then I can replace this directly using pxt, because in here we took this relation. So this is pxt, and if I differentiate it with respect to t, this is 0, and this gives fxt, simple fxt. So the negative value comes from there, and this is directly denoted by pxt. So this ratio is also used to define the force of mortality. And we have the number of survivors at time t, and then the same quantity can be defined using the number of survivors like this, because we know that this one is given in here, Lx plus t divided by Lx. Lx is a constant for both cases because it doesn't include any part from t, so that we can cancel out those things and have this form for the force of mortality as well. So considering these, time to time, we will use this relation to get the expectation or expected values for future benefits and premiums. So then I can write it down using the actuarial notation that the probability of surviving for t more years for person age x, and the force of mortality at x plus t. Then I can move to define the survival probability for n years using the force of mortality. So it is the exponent of the integral from 0 to n, and we will integrate this function with respect to t. So that is the definition for probability of person at age x surviving for n years. And so this is in terms of the future lifetime. So I can use the same exponent and write down it, just doing the maths to replace x plus t by y, so x plus t is denoted by y now. That means I have changed the variables, and these are, so 0 and n are the points on the future lifetime random variable. X and x plus n are on the points, or which means are on the line for the real lifetime, or this is the real age now. So that is how we can define the survival probability for n years a person who has age x using the future lifetime and the force of mortality, or the actual age and the force of mortality. So those are two equations that we can use. And for this force of mortality, we have two properties. It is a non-negative value. And if you integrate this from 0 to infinity in the future lifetime, it will goes to infinity. That means this one is increasing over the time. That is, this is a good point to think about this force of mortality. We know that when we are getting older, so the death probability increases. So that is the concept. And now we know many things about the probability related things. Let's discuss few points related to the change of the force of mortality. We can do the changes in two ways. First one is I can modify the force of mortality by introducing a constant to the existing force of mortality. That means we are adding some risk to the existing risk, and it will give us a new survival probability. And if we use this definition, I can write down when we modify, which means add a constant risk to the force of mortality, I can interpret the new survival function as a multiplication in between the previous survival function and a constant given by the exponent of kn. So that is called, we call this as adjusting force of mortality. So we add a constant to the force of mortality. So it is called as the adjusting force of mortality. And we can modify it in another way. Have the force of mortality, and I will modify it by multiplying it with the constant k. This will lead to have a new survival distribution, which is defined using the previous survival distribution. Now it is as an, which means instead of the exponent, we have now a new power for the previous survival function. And we call this one as adjusting mortality rates. So these are the two incidents we can modify the force of mortality. And the other one is age rating. So this concept doesn't modify the force of mortality like adding a constant or multiplying a constant. It says I'll give an example in terms of the number so that you can digest it, the concept. Suppose we are adding 7-year age rating to a person at 40. So this means the person at 40, so this is the real age. Age is 40. And by the time of purchasing the insurance, we consider this person as a person at age 47. So the actual is 40, but due to some previous exposures of that person, we consider him as a person whose age is 47. So that is the age rating concept. So this is the present age, but he is considered as a person at age 47 at this time, because we can say that person is working on the road, so that person has an exposure to hazardous elements, and we cannot consider this person as a person who is at age 40, but we will consider at age 47. That means that person is in a more riskier situation than the others who are in his cohort. So if I take 10 people from the same age, this person has a higher risk of mortality than the other 9. So that is the concept of rate aging. So in that case, we don't need to adjust these cause of mortalities. We are just referring to the rated year, and we will do the calculations considering him as an older one than he is. So that is how we can think of modifying the risk. And now, since I have this relationship, I'll be using that and define the 3 probabilities at the survival probability for T years using the density function. So this means survival for T years. That means the death occurs after T years, and we have to consider all the probabilities. So I can write down, this is same as taking the survival probability by integrating the density function, which can be written in terms of this actuarial notation. And for the death probability, that means the real age is T and death occurs within the next T years. So the future lifetime goes from 0 to T, and the density of the future lifetime is P x and mu x plus S and D S. And for the deferred death probability for a person at age X lived for few years and death occurs within the next T years, is integrating the density function of the future lifetime from U to U plus T. So since it is for next T years, that means in the number line, U and then adding more T to the previous lifetime. And we have the same density function the person is at age X, and the force of mortality is this. So I can write down these functions like this. So that is how we can define these probabilities. That means the death probability, the survival probability, and the deferred death probability. The next thing I can do is now I know how to calculate probabilities in many different ways. Then I can define the movements for these probabilities. Those are the things I need, because then I can take decisions based on the probability and also the distribution, the entire distribution, by referring to the movements. So for the movements, again, I can say the complete expectation. So in this case, I'm considering the lifetime or time to death is continuous. So I can have the first movement denoted by the X, and since it is continuous, I have a small circle on top of E. It is defined as the expected value of the continuous future lifetime for a person at age X. And it says this goes from 0 to infinity. And this one can be replaced with this is the maximum lifetime, and you have to deduct the current age from the maximum lifetime. So this gives the remaining lifetime. So you can replace this one. If you know this maximum lifetime for this population, then it is t times f, simple f of t, which can be written using the survival probability and the cause of mortality. And we can apply the integration by parts and get the final form in a simpler version, which is quite easy to work with, where we only have the pxt notation, which is the survival probability, and we are integrating that survival function from 0 to infinity to get the complete expectation. So this is the future expected lifetime for a person at age X given their population, the distribution knowledge of their population. And then if I can define the second movement, then we can use these two to get the variance of this random variable. So I can define the second row movement of this as integrating it from 0 to infinity. Since it is second row movement, this is the definition for taking a movement from a distribution. Then I can simplify it to a version where it only uses survival probability. Then using these two, I can define the variance of the future lifetime when it is continuous as this. So this is coming from the distribution theory. So this part is E circle X squared. That is in terms of the actuarial notation. So this is the complete expectation, and we know that we introduced the concept of current expectation because in practical situations, we have benefits paid at discrete time intervals, and also the premium is also paid in discrete time intervals, so that we love to work with current random random variable, so that we need to get the current expectation of that current random variable. So the first movement is given at EX. Now we don't have a circle. That means this is the discrete version. If you have a circle, that is the continuous version. And since this is the expectation of Kx, which is the coordinate random variable, and it is discrete, so instead of the integral, we have the summation, and it goes from 0 to infinity, and the value is k. And always it has this deferred probability. That means we know the person survives for k years and death occurs within the next year. And also for this one, we can rearrange it and say, starting from k1, this is same as taking the summation of the survival probabilities. So instead of t, now this is k. That means survival for the first year, second year, third year, fourth year, like that, taking all the survival probabilities and summing it up. So it will give the first movement. So now you can see the similarities that in here also we are integrating it. In here we are taking the summation. The integral start from 0 to infinity, summation start from 1 to infinity. So that is the difference. And in a similar way, we can have the second movement, which is the expectation of kx to the power 2. The definition says, again, k start from 0 and goes to infinity. And since it is second movement, we have k square. And the probability is a person at age x survive for k years and death occurs in the next year. So this is also simplified to a version which is a sum from k1 to infinity. And now we have 2k minus 1 times the survival probability. So using the summation or series, the concepts of series, we can simplify from this version to this version. And using these two, I can define the variance of the coordinate random variable and say it is like this. So this is how I can define the variance. And now let's move to a different, the same concept for a different modification. So here it is complete, and coordinate also consider the lifetime up to the death or the maximum life probability or the time point where the maximum can occur. But we know for some products, the coverage period is limited. So that means we have to use only a part of the life distribution. Then we have take the expectation for temporary part, and we call that as the temporary expectation. That means we are only considering few years from now because the product validity is only for that period. Suppose we are only considering the next n years. Then for a continuous life, age is at x and we are only considering n years. So this is the term. So if you have this angle n, it says the coverage ends at n years from now. Since it is continuous, we have the circle over E, and this is the expectation of minimum of Tx and n. That means for the first 10 years, we have Tx. After that, it is n because we don't care about the life after n years, which means we don't have a record of the status of the lifetime after n years. Now, we are only integrating it from 0 to n. And within that period, we have to use the density function. But after that, we know the person has survived, but we don't know what happened and at what time the death occurs. So after that, it is n with the probability of surviving for n years. That means this probability contains all possible events after that. And this also simplifies to the previous 4. So it is easy. Now you can see if it is complete, then n is replaced by infinity. If it is term life, then it is called the temporary expectation and it is limited to n. And for the temporary expectation, we can get the curtailed one. Still, the notation is same for the subscript, starting at x and goes to n more years. Since it is curtailed, or discrete, we don't have the circle over e. So it is the expectation of minimum of kx or n. That means after n years, we don't know the actual status. So we only know that that person survived for n years. The summation goes from k0 to n minus 1 because the curtailed says the integral part or integer part. So it goes to n minus 1. But since it is starting from 0, we have n terms of summing in here. So the value is this one, and the person at age x survived for k years and death occurs at the next year. And we know after n years, it's always n. So we only know about the survival status of this policyholder up to n years. And interestingly, this is also simplified like this. So it says the summations of survival probabilities from x to 1 year, x to 2 year, x to 3 year, up to x to n years. So that is the series of summation in here. And the difference is if it was complete life, which means a curtailed lifetime from now to the death, is start from x and go to the infinity. But yeah, so k is equal to 1 and go to the infinity. But if it is limited time of coverage, that means starts from 1 and go to the maximum number of years covered. But still we are summing up the survival probability. So that is the pattern you need to catch. And now the next concept is we have relationship between EX, which means the complete future. So I think it is not from here. So we don't have to worry about calculating these two, which means in two separate occasions. We can define a rough approximation for the complete expectation and the curtailed expectation like this. The approximation says the complete expectation is approximately equal to the curtailed expectation plus 0.5. So that is when we are using a discrete random variable and finding the probability using a continuous distribution. So you have to adjust the discrete value by adding 5 or subtracting 0.5. The same concept, a similar concept, not the same one. So here, this is an expectation. So you can approximate the continuous expectation, which is the complete expectation, by adding 0.5 to the curtailed expectation. So we can move to some recursive formulas of these expectations. So if I know the expectation at edge x through recursive formulas, I can calculate it for the x plus 1 or x plus 2, x plus 8. Like that, I can repeat it for many upcoming years without using the fundamentals again. So I can say the complete expectation at age x can be written in terms of the continuous expectation for n years, that is the temporary expectation of a continuous random variable. And if that, so we know that after n years, if that person survives for n years, I can define another complete expectation. And now that person is age x plus n. So that is the meaning of this recursion. And I can use the same concept for the current expectation. Now the person is at age x, and this is the expectation by considering all the values from tx equals 0 to the infinity. And I can represent this using a temporary expectation for n years. And if that person survives for n years, then will be a new expectation, and the person is now at age x plus n. I can do the same thing for the temporary expectation when it is continuous. Person is at age x, and we are thinking about m plus n more years. And if m occurs before n, that means I can break it down to two temporary expectations. First one is 0 to m, and now this person survives for m years. So I have only n more years, and the age is now x plus m, and terms are left for n years. That is for the continuous. That is why I had small circles. Using the same notations without circles, it says we are using the coordinate random variable and surviving, which means now we are considering from age x to x plus m. And we know the person has survived for m years now, and we have n more years, and the age is x plus m, and considering the rest of the n years in here. So using these two, I can refine another one. So the concept is, if I have a current life expectation, so these surviving for 1 year's times 1 plus x plus 1 d. So this says the current expectation of a person at age x, and if that person survives for 1 year, so it is 1, and at that point I can start another expectation because the life has survived 1 more year. Now the age is x plus 1. So if I calculate this, and if I know the survival probability for 1 more year, then I don't need to calculate the expectation for x plus 1 years by taking the long summation. I can just use the recursive formula and get this value easily. So that's it. That is defined for current expectation. And now we can go for some mortality loss. So in this course, we used two special cases. That first one was constant cause of mortality. So by the definition, we saw that it was a function, and actually it is a function of t. And if it is a constant, then I can replace that notation using mu only, because it says now we don't. So this quantity doesn't depend on the time, but still it is positive. And then we know that we could get the probability of survival for t years, like the expectation or the exponent of the integral, and taking the negative value of the integral. So since mu is constant, that integral gives us mu t. So negative mu t is the exponent part. And for the complete future lifetime expectation, it is just 1 over mu. Because for this one, it's px. We know the pxt. Pxt is this. So if you integrate the e to the power minus mu t, you will get 1 over mu. And for the temporary expectation, for n years, I can say it's 1 over mu times 1 minus e to the power minus mu n. That is how I can simplify these calculations using assumptions. First one was the constant force of mortality, and this is not valid in practically most of the situations, but when we are calculating, we are doing approximations. So to approximate that, sometimes we may have to make these assumptions at some point of the calculation. So first one is the constant force of mortality, and the second one is the uniform distribution of death. So uniform distribution in here. That says the number of survivors can be written like the constant times the remaining lifetime. It will give us the force of mortality as 1 over mu x. And if we need mu x plus t, since this is uniform now, it's mu x plus t. So we can easily modify it. So depending on that, I can define the survival probability like this. We know that you can define it using the number of survivors, or the ratio of the number of survivors in 2 different time points. And by replacing LXT, I can have mu x plus t over omega minus x. And for the death probability, it's the difference or the number of deaths between x and x plus t, and divided by the number of survivors at x, and it will give us t over omega minus x. And the other one was we are thinking about deferred death probability. So the person has survived for u years. So the survivals at x plus u age and survivals at x plus u plus t divided by number of survivals at u this also gives same probability. And the complete expectation is just expectation of a uniform distribution, which is, we know that the 2 points, or difference of 2 points divided by 2. And for the temporary expectation for n years, it's surviving from x to n, and at that point it is n, and death occurs during the next n years, and the weight is for that one is over 2. So that is how we can modify these probabilities under again, I got disconnected. I think now we are okay with recording. So we can start from where we left. And the other two was using Gompert's law to modify the force of mortality. That means the force of mortality was defined using 2 constants. And the survival probability was defined accordingly like this. And this one will be provided in that equation, so you don't need to worry about these 2 equations. But just to remember that we have 2 laws that we can modify the force of mortality, and these 2 we can define the survival function in many ways. Now you can see under these 4 different assumptions, so we had different values for the survival function. This equation is also provided, so you don't need to worry about memorizing it. And now we always, which means we discuss these things only for, which means always consider the annual events. Now we can think about what if we consider it for months, or what if we consider it for quarters. Then we need the fractional age assumption. So we can move to fractional age probabilities using these assumptions. So in here we use UDD, which means the uniform death distribution, and the constant force of mortality. And we use the UDD where the factor. So now the T is a fraction and it's between 0 and 1. So if the distribution is uniform, we can, under this assumption, we can say x plus t, yes, which means this is like 30.5, which means full 30 years and 6 months. So we can find it using complete years. So we multiply 1 minus t from present survivors and multiply t by the next year survivors. And the best point you need to memorize is the death probability, which is the age is X, and death occurs within the next 6 months or next T fractional years. It's just multiplying that fraction from the death probability for the full year. So this is the important relation we need to get out of this UDT. Whenever you are said to find a fractional probability under the UDT, just multiply the annual probability from that fraction. So in here, X is a complete year and T is a fraction, which is in between 0 and 1. And we can have another fraction on right-hand side as well. That means a person has survived for 30.2 years and we need the death probability for the next 0.5 years. That means the death occurs between 30.2 and 30.9. So we can say another fraction in here, and we have another fraction on the left side as well. So it's T times QX1 and 1 minus S times Q. That is, so this is valid under this condition, where these two fractional ages should sum up to 1 or less than that. So in here you can see, this is the death occur, or the probability of death occur from a person who is at age X to the T years. And this is surviving from X to S. So the survival probability can be written as 1 minus the death probability. That is how we got this one. And the force of mortality at this, under this assumption, now T is a fractional age. So it is the full year death probability divided by the survival probability. And the survival probability is 1 minus death probability. So that the death probability, again, the fraction times the annual probability. And the PDF is also defined. So in the same notation, but previously this T was annual. Now this T is fraction. That is the difference. But now, since we are using this UDT, it is a constant. So throughout the year, it is same. And we have the complete life expectation. And under the UDT, it is equal to the current life expectation plus 0.5. In general case, this is approximated, but under UDT, it's directly equal. And also, we can write down the complete life expectation, like 0.5 times the annual death probability for a person at age X, and death occurs within the next year, and the survival probability plus E X plus 1. This is a recursion formula. So this is only for your knowledge, but you can define these things by yourself if you need to use it in somewhere future, because it's just considering the life distribution in between X and X plus 1 is uniform. So the next assumption, the common assumption, is constant force of mortality. So when that happens, again, the fractional life is in between 0 and 1. I can write down the number of survivors at x plus t. That means, for example, again, 30.5. The 30 is x and 0.5 is t. And since it is constant force, I can write down 1 minus t is the power for the present survivors and the next year survival as a power of t. So in here, it's a summation for UDD. Now it's a multiplication with power. And similarly, we can write down fractional survival probability as t. So if UDD, we can modify the death probability. If constant force of mortality, we only modify the survival probability. So if you need to find the death probability, you should get 1 minus the survival in terms of this px1 to the power t. And the force of mortality is minus ln, the annual survival probability for the next year. Similarly, we can use the same notation for the density function. And now this is constant and this is came from here. Yeah, so this is the exponent under the definition that is the negative integral of mu x plus t, since it is constant. So we can get that easily, like e to the power minus mu t times mu. And then there's another concept we discussed. For the select and ultimate mortality. So for the select and ultimate, it's like this. So under different conditions, when we are offering the contract, so we are considering that person has a different mortality than the general population. So you can remember, we call that extra mortality risk, that age rating concept. So like in here, when you are doing the underwriting, we know that, so we know at the company, there's an underwriting effect for this policy for this much, like if you're buying the insurance for 20 years, and so we write the policy affecting the first 3 years under some special conditions, taking into special conditions. And during that first 3 years, the mortality is different from the general population of the same age. So then we denote the select age like this. Select age is this. This means the person buys the policy at age X, but subjected to some conditions. So this indicates that there's an effect on this purchase for this person at age X. So that we can denote the death probability like this. So if this notation happens, this says it's still under the special condition period. And once it's over, so this is under conditions. And once it is over, after the period, the death probability is same as the general death probability. So that is the special case. So the table says we will find a table like this. Suppose the selected age is only for 2 years. So then this says during the first year, we take this one and move to the next. And if it is age 31, still we are using this. And then we move to here. And you will see the number in here is same as number in here. After that, we will read the numbers. And if the person buys the product at age 30, so this point, it is 30, 31, 32, and the person's actual age is 33, but that debt probability is corresponding to the general. So in here, you will see on the right-hand side, it will be like this. So this is the death probability of a person who is at age 33 in the general population. So this is how we can read it. And those are the things that we need to remember in terms of referring or generating the probabilities from this distribution. We need probabilities because we need expectations, and also we need expected values of different payment schemes. Now we are going to discuss those things quickly. In insurance, so there are two types of cash flows, basically. So we buy a product at age X, and the TX start from there at 0, and we will pay some series of payments, and we call it premiums. And these premiums can be equal premiums or a different special premiums. And the benefit is only paid at once. So suppose at this point, the death occurs, and there are different types of policies. If the death occurs at this time, some policies pay the benefit at the point of death. Some policies pays they pay the benefit at the end of the year. The premium is paid at the beginning of the year. That means if the premium is paid, we know that that person has survived up to, suppose in here it is 3. So if I pay the premium at the beginning of the 4th year, that means I have survived 3 years from the purchase. And likewise, it's go to some period. So some premiums can be paid for long time period, or some cases it can be a lump sum at the beginning, or it can be a deferred payment scheme. It starts, so you buy the product in here, but pays the premium from the 5th year to the 10th year. So the benefit also, which means defined in terms of different ways. So if it is the benefit payment at the time of death, it's a continuous case, and mostly it can be paid at the end of the year of death. So then it's discrete, and there are some cases where which means we can restrict the coverage period. So we call it term life, and even for the term life, we can have a death benefit, or if that person survives the term, so then we can pay a survival benefit. So there are few different combinations. So all these cases, in terms or in the point of view from the company has to pay this benefit amount, which will be paid at one point or at one time on the timeline. And the company will have cash inflow through the premiums, which can occur at one point or through several points on the timeline regularly. And this benefit can be a constant benefit, which means they pay the same benefit regardless of the time, but also it can be a benefit which increases with the time, or this can be a benefit decreases with the time. So those are the many possibilities we can think. For all these things, we can uh, calculate a present value because as the company, we don't want to, so we are doing a business and the company wants to uh, like this. They don't want to make profits, but they don't want to lose money. That means the basic concept is if we are giving B, so then we have to collect B. But we don't know the actual time point where we have to pay the B. So till then we have to get some cash inflows to meet this cash outflow requirement. So since we are still on this point of the timeline, these are also all these payments. So these premiums paid in here are in future. We only have the plan, but we haven't collected it or we haven't paid any amount. So what we can do is consider all possible outcomes and get the average. So then the present value uh, random variable can be, so present value become a random variable because we don't know the value, exact value, but we know the whole possible values for that variable. So it is random now, and the best way is we can incorporate the probability and take the expectation. So we can have an average value for benefit and the premiums so that we know we are not going to lose money due to this or due to taking this risk of someone else. So that is the concept. Then we can quickly go through 5 policies for the continuous case, and we will have present value random variable and the type of insurance and for this one the present value depends on the discreteness, or which means the type of the random variable. So we can consider it can be discrete or continuous. And for each of these present value random variables, I can again for discrete and continuous take the expected present value. So those are the all possible measurements I can consider in this under this topic. So first one is the whole life. That means if I buy the product at this point, this validates the coverage periods validates until the death occurs and there's no time restriction. So if it is discrete, the present value random variable should be AX plus 1. That is the discount factor. And we define this for $1 benefit payment. But in general, the benefit can be a different amount, but we consider them to be net value. That means regardless the time point, the benefit is same. And the appropriate discount factor, which is this, which means this benefit payment occurs in future. So we have to get that back to the present time point, which means discounting it back to the present time point for the discount factor in each interest theory. And then to get the expectation, we need to find the probability of surviving up to that point, or probability of death up to that point. So since these are benefit payments, always we work with death probabilities, because when the death occurs, the benefit occurs. So now for the definition, we consider that the benefit is 1 and the discount factor is this. So we have multiplied the benefit times the discount factor, and it gives the present value. So it validates for all the other policies as well. The condition is this has to be positive, and if it is continuous, then the benefit is paid at the moment of death. So this is positive, and benefit is 1. So 1 times the discount factor. And for the expectation, we need to consider all possible values that using the probability. So now to get the present value, so we will sum up all the possible values of K, and we will multiply the benefit and the discount factor. Since the benefit is 1, we only see the discount here, but we know the benefit is B. So then you have to multiply B and the discount factor. And we know that since it is discrete, or it is the quadrate random, the person has survived from X to K and death occurs in the next year. So this is the notation. This says capital A. So it is the actuarial present value or the net single premium for the benefit which is paid at the when the death occurs, and there's no coverage limit, so it is a whole life. And the person has bought this contract at the age of X. And if it is continuous, for the same notation, we have a bar over A. It indicates it is continuous. And since it is continuous, it goes from 0 to infinity, and we integrate the distribution, and 1 times the discount factor, and we know we have to integrate the density function of the future lifetime, which is accessed through the multiplication of the survival probability and the force of mortality. So that is for the whole life. And the other type is N-year term life. So for the term life, it's restrict the number of years of the coverage. So now it starts from the beginning, the coverage value is only for N more years. So I can write down the present value. So within the first N years, there's a payment. After the N year, there's no payment. This is for $1. And the continuous case, same. Now we are using TX, and there's no payment after the coverage period. And we denote the actual present value for this one. It's this. Age is X, the term is N, and we have 1 over the X to show that it is a term life. That means There's only benefit payment, and there's no survival payment. And since this is 38, it goes from 0 to n minus 1, and we have the same structure in here. So one can write down these two using previous notation. That means this is the actual present value of a whole life, and if you remove another whole life insurance present value, which is at x plus n time point. So this is in future. That means you have to discount it back to the present, which means at age x, and this present value is away in years from the present. So we have to take it back to the present. And this is called an endowment term, which will be defined in the next few steps. And for the continuous case, we have a bar over there, and we have the same notation apart from that, and we will integrate it from 0 to n. And for this one, again, it is same. And we can write it down using the whole life present values and the discount factor. And now we can consider n-year deferred whole life of $1. That means the coverage period starts after n years, and it is valid for the rest of the life. So if it is discrete, it says during the first n years, there's no payment, and a payment can occur after that, and we will discount it back to the present. When kx is less than n, this is n, and kx is greater than or equal to n. And if it is continuous, we have the same. And this says tx is less than n. This says tx is greater than or equal to n. When we are taking the present value for the discrete one, says purchase at x, deferred for n. And says the present age is x, and the coverage starts after n years. So I can write down this using the previously defined policies. So we have the whole life, but this notation represents the entire lifetime from x to the maximum age. So we don't care about the first n years, so we have to remove the effect of the first n years. So that is the present value of n-year term life. Or we can consider that the present value at age x plus n, but we are on point x. So we have to discount it back. These two cases, the equations provide the concept. And when it is continuous, person is at age x, a bar represents the continuity and deferred for n years. The same notation applies. Continuous whole life present value, and we have to remove the continuous n-year term life present value. And also, if we can discount back a future present value at x plus n, which is a continuous one, we can have the same present value in here. That is another way. So for some cases, there's no death benefit during the coverage period. There's only one survival benefit. And we know that that payment occurs when the person survives for n years. So it is called the n-year PO endowment. So these are all, so these are the insurance products, and we are defining them in terms of the benefit payment. And next we will be defining the premium payment scheme using annuities. And then we will use these two together to define the net premium. So that is the motive. So for this one, there's only one payment at time point of n, and there's no payment before that. So when kx is less than, there's no payment. When kx is equal to n or greater than n, there's a payment at time point n. So it is Vn. And for the continuous case, it is same because there's only one payment regardless the discreteness. There's only one at time n. We know that point, so we don't want to care about the type of the random variable because we know the time point this payment occurs. It is n. And we can write down it for both cases. It is x for n terms, but the payment occurs at the end. So that is why. So in here, the payment occurs during the life. That is why we put 1 over x. But this is, in this case, the payment occurs at n for sure. That's why we put this 1 over n, angle n. And I think to make it more easy, I will remove this one. So now you can see for both cases, we have this one. For dx is less than n, dx is n. So it's valid for both cases. And this is valid for both cases, which is denoted again using this notation or discount it back from n years. We have to survive for n years. So all these three terms have the same mean. And the final one is using the PO endowment and the term life, I can define n-year endowment insurance. So in the n-year endowment insurance, we have a death benefit during the first n years. Benefit is 1, that is why we had 1 times the discount factor. And after n years, if that person survives for n years, there's a survival payment, which means if the death occurs, there's a payment. If there's a survival, then there's a payment, which is $1. But in company's account, there's only one payment. It can be, the type is different, a death or a survival. But in here, it is $1. That is why we have the same cases. But in practical, the death benefit can be a different amount and the survival benefit can be a different amount. So this occurs when here. And if it is continuous, the payment is made at the moment of death. So it is Tx, and the survivor status is at Tx equal n, and if the person survives beyond that, the payment is made at the Tx equal n, which is the discount factor is now taking the payment back n years. So it's the end of this one. So we have two present values. For the discrete case, start from x, goes for n. We don't have any 1 here because we have two payments, two possible payments. First one is paying for a debt from x to n, or paying for the survivor status at the end. So this is the notation. Or for this one, you can replace this n, because this is the notation you can find in the sorry, life table. And if it is continuous, the subscript is same. We have a bar over a. This one is just represent one payment at a fixed time point. So we don't have a bar because it is discrete. That's why we had only one equation in here. And again, this. So that is how we can define the 5 different benefit payments. And you will have increasing and decreasing situations depending on the type. So I'm not going to recall those things. Yeah, but yeah, I'll recall some of them. And so we can have increasing. So that means by the time, the amount paid as the benefit increases. And there's no bars, that means the increment happens at the beginning of each year. So it's like a step function now. Person is at age X, and this says annually increasing insurance, whole life insurance, and this is the expected value of expected present value of the future benefit payment. We don't know the exact time, so we have to consider all possible times. And since it is an expectation, the benefit amount is k plus 1 because it is increasing. The discounting factor for the time is this, and the benefit is paid only if the death occurs. So the deferred death probability should be there. And the same counterpart of the increasing whole life for a continuous insurance, that means the benefit is paid at the moment of death. So we will have exactly at the death, we will have a benefit payment. And for this one, this is the discount or the discounted or the present value of the benefit, and the density function is taken using this. And this is annually increasing. And this is also the same case. And we can have annually increasing term life as well. So the notation is like this. And since it is term life, the payment only occurs when the death occurs during the protected period or the coverage period. And the summation goes from 0 to n plus 1, but the term is same. The continuous annually increasing term life, this goes from 0 to n, the payment here. And we will have fxd with this. And now that is increasing. So we can have a decreasing one as well. So which means with the time, the amount paid as the benefit decreases. So it starts from annually decreasing $1. So which means the dollar payment proportional to the number of years we have. So it starts from a lump sum of n years for a term life. And then this should be limited to, because we have n years, this should be limited to n-1 summation. And the rest is same. So we will have the same probability here with the discount factor. If it is continuously decreasing term life insurance, instead of t, now we have n minus t. The rest is same. And if we add the decreasing term life with the increasing term life, so that means these two, you will see, you can cancel out k because the summation has the same number of terms. So we will have n plus 1 level term life. For the continuous case, decreasing continuous term life, increasing continuous term life gives us n times a level term life. So those are the things that we can record. Then, as I mentioned, this term is a widely used term, which is the present value of an PO endowment, or discounting $1 payment, which is ahead of t years from now. So we can write it like this. Since it is $1, this is the discount factor. And since that person has, which means the payment is made t years from now, to get this, that person has to survive t years. So this is the present value, the expected present value. So this is the present value. When you are multiplying it with the respective probability, this will become the expected present value. So when you have the life table, you can calculate this using this. Also, if you have two time points on the timeline, like t and h, you can multiply it. If t is the first time to meet, so then discounting it from there, and that person has already survived x plus t years and has to survive h more years. This is of decomposing it. And if we want to get the variance, then we need to get the second movement. So second movement is denoted like this. It says Vt. So this is the present value random variable. Since the second movement, you have to square it. And this is the probability, which is replacing 2t and pxt, or Vt, and if you 1 Vt, it is ext. So you can play with that. Also, if you replace this pxt, you can say it is v2t lx plus t over lx. So there are many different phases for this. And also, in terms of insurance, the PO endowment let's write it the other way. PO endowment is the difference between present values of endowment and no, I think it's better right the other way. The endowment is term plus the PO endowment, which is same as this. So those are the possible notations you can see. And also for term life, it's removing the effects of future present value from the whole life. So this is how you can replace or represent a term life in terms of endowment and PO endowment, or a term life with two whole lives and a PO endowment. And if we have two assumptions, constant force of mortality or uniform distribution of death. So we know that we can modify the force of mortality from there. Then we can say for the continuous whole life, the present value is given like this. But under the UDD, we can denote it using continuous annuity payment for the rest of the life over the remaining life. And for the term life, when constant force occurs, it's the present value of whole life, but we have to adjust it for the coverage period. And the same quantity under the UDD, it is annuity for years and the remaining life. For the PO endowment, it's plus delta over N. And under the UDD, it's discounting the remaining life from X plus N years and the remaining life from now. So those are the modifications we can do when we have these two assumptions. And then to calculate the variances of these policies, we have to just adjust. So I will write down it only for two cases for the whole life. You can write down the discrete using this is the second movement of the expected present value, and this is the first movement, and this is the variance. And if it was a continuous random variable, the same notation, but we have a bar over A. And to calculate this second movement, you just need to replace delta with 2 delta in AX or A bar X to get 2AX or 2A bar X. So that is how you can get this one, which means if you know this one, you can get this one by replacing delta with 2 delta and so on. So this is valid for term life, deferred whole life, and endowment. And in special case, in the pure endowment, since we have only one payment, this one is the variance is the second movement minus the first movement square, and you will see that it is replacing t by 2, which means previously it was Vt, now it's V2n, and surviving for n years times death occurs within n years. So that is the special case. So it is also can be replaced. You can access that by replacing V with V2 or I with 2I times plus I square in the definition. So that is how you can access these things. And now we were discussing all these things for annual insurance. Let's discuss some special cases for monthly benefit. So that means instead of the annual payments of benefits, now we can divide the payment time into small intervals, months or quarters or half years. So for the monthly insurance, since now it becomes discrete, the Curtain tandem variable shows like this. This defines you have the future lifetime times the actual terms and then get the integer value of this multiplication. Suppose this is 30.5. So then we take the 30.5 and multiply it by, suppose we are interested in half year payments. So M is 2. So 2 times 30.5, it is 31. And the integer part of 31 is 31 itself. And then we will divide it by 2 again to get this KXM, because it says how many half years we have. So this is the definition and the probability is taken. So now this is not K, this is R, because K is for annual years, but this is something for this. So if it is M is 2, it is half years, M is 4, it is quarters, M is 12, it is months. So it depends on the scale. And says the probability of X age survive for R units, and the person who has survived for R units, death occurs in the next this much of quarter years or the partial years. So since this is M is 2, this is half a year. And it is same as the deferred probability of a person at age X surviving for R time units, and this R is a collection of 1 over M time units. So this says R is how many 1 over M time units we have. So if this was 12, M is 12, R is number of months from the purchase to the death. So it's like the scale has a different value now, but the amount of benefit is $1 still, so that I can say the present value random variable is now defined using this implicate random variable. Instead of 1 now, I have 1 over m. And the benefit is 1. So that's why the present value is this still. And this is positive. And for the whole life, it goes to infinity, starts from 0, and it's k plus 1 over m. And because if the death occurs, the payments occurs at the end of that quarter period. So which means if it goes half year, so if the death occurs within the first 6 years, the payment is made at the end of the 6th year. And like that, it goes from half to half. The probability is surviving for k over m time periods, and death occurs within the next 1 over m time period. So that is for whole life. And if it was term life, so then this is for whole life. If it is term life, we know we have two cases. For the covered period, we have the same thing, but we don't have a payment after the coverage ends. So this one says to be specifically, so now it is a discrete random variable that I can say it's 0, 1 over m, 2 over m, up to m minus 1 over m. And for this one, it's equal to n m plus 1 over m, like that. And present value is this person is at hx, the value for k amount of 1 over m cases, and death occurs within the next 1 over m period. So those are the adjustments we can do. And now under the UDD assumption, I can relate the continuous whole life present value to the discrete whole life present value like this. And for the term life continuous case, the continuity adjustment is I over IM. So this is for the adjusting M to whole life. So this is like this. Since it is continuous, we have delta, and N, this is discrete. And for the deferred whole life continuous present value, it's I over delta, and the discrete case. And for the endowment insurance, the adjustment only occurs for the term life, and the pure endowment part is only one-time payment at fixed time point. So then it's not adjusted because we know that it's fixed at time scale in future life. So when you are adjusting the discrete life to an empty life, you just need to multiply that by this factor I over IM and get the annual rate in here. So as it is previously said, replace if you want to get the second movement, that means to get this, replace delta with 2 delta in this. And for any other, it's value. Or if you want to get this, you can use the effective rate of interest like this. So those are some examples you can use. And now we can move on to the annuity part. So in here, as I mentioned, so the annuity is for benefits payment. So throughout the annuity, we take the present value of the benefit payment. So, sorry, it's not benefit. The previous one was for the benefit payment, and this annuity is for premium payment. So this one was, so up to this point, these capital A's were for benefit payments, and now we are shifting to simple A's, which those are for premium payments. And as I mentioned, the premium is paid at the beginning of the year, and it is a series of payments. So this premium payment process, since it is a series, we have $1 at the beginning of the first year, then another dollar at the beginning of the second year. Likewise, it continues up to the term ends or death occurs. So when we are taking the present value, there's an amount paid as the premium, appropriate discount factor considering the time which is where the payment is made, and a probability corresponding to that event. So the benefit is paid when or only if the insurer is alive. So that means we need the survival probability of that time. So I can say, so these are corresponding to the premium payment series, and the benefit, I will use the red line. So for the benefit, because there was only one benefit, but the premiums, there's a series of premiums. So let's summarize it again. So we have two types of annuities: the annuity due and the annuity immediate. The due is a series of payments start from 0. Immediate is a series of payments start from the end of the year. So in annuity due, if the period is end, the due stops before, which means which the last payment is made at the beginning of the end year. For a immediate, the first payment is paid at the end of the first year. That means the last payment is made at the end of the last year. So which means in here, we don't have a payment, but for the due, at the beginning, we don't have payment for the immediate, and for the due, we don't have a payment at the end. So we will use, since the premium is paid from the beginning of the year, so we will use annuity dues. So the type of annuity, the present value And we have discrete and continuous. And again, for the discrete and continuous cases, we have the expected present value for discrete and continuous. So if we have a whole life payment of $1, okay, I'm back again. And yeah, so for the whole life, it's like this. We have the series of payments and it's due. We have two dots over simple A and the payment stops after K plus CS. And if it is continuous, you have a bar over A and you have TX instead of KX. So the present value is two dots for the whole life at X, and you have to take the summation from K equals 0 to infinity, and discount is VK. The payment occurs when the person survives, so we use the survival probability. And for the continuous case, we have bar over A, and we integrate it from 0 to infinity, and we need the survival probability. So for the benefit, we use death probability. For the annuity, so it is the premium. So then we use the survival probability. So this is about the cash inflows for the company. And for the N-year temporary life, that means the payments are made only for N years. So in here, the payments are made till the death. But now in here, the payments are restricted for N years. That means we have two options. This part is same as the whole life. But at the end, if that is survival status at end, so then for sure we have N terms of payments. And for the continuous case, it is again the annuity for TX and the annuity for TX equal N. That means N terms. And for the present value, it is two dots X to N. This goes from K equals 0 to N minus 1. This is same as in here. And for the continuous case, the integral goes from 0 to N. But this one is similar to here. So you can write down the same thing in terms of the whole life annuity at X and X plus N using discount factor like this. And for this one, it's bar X, the discount factor, the present value, so now it's a continuous case. So you have a bar instead of two dots. And we can have another one called N-year deferred whole life. In that case, there's no payment up to N years. After that, we will have series of payments. discounted by VA. And for the continuous case, 0. And for this one, Vn x dx minus n. So the discrete present value for the deferred life is x deferred for n years, and summation starts from n goes to infinity. And we have the same thing like in here. And for the continuous case, the notation changes from 2 dots to bar, and the integral goes from n to infinity, but this part is same as, which means integral, the limits changes, but the other parts are same. And the final type is in near certain and life. That means we have two parts for fixed period. Definitely, we have a series of payment, but after that, it continues till the death. So which means for the first 10 years, regardless of the death, we have to pay. But after that, we have to pay until the death. And for this case, in the continuous notation, for this one, it's n. And for this one, it is dx. These are the present values, but the actuarial present values are denoted like for the discrete case, we have 2 dots, and this is for the term, and this is for the whole life. So that is how certain and life is defined, and we have a term life inside it and a deferred whole life after that. And for the continuous case, it's bar, and x to n is a term, and then a whole, so which means a summation of term life plus a deferred one. So that is how we can relate these things. And now we can have the same annuities concept for varying annuities like increasing and decreasing. You can use the same notation and replace the respective probabilities for here, and you can see you can define the same set of equations in here. The only thing you have to replace is you will replace this death probability by the survival probability, and if it is, so instead of this capital A, you have to use A double dot, simple A double dot for annuity dues, and simple A bar and I bar for continuous cases. So all these are valid by replacing. So you just have to replace the probability and the notation with 2 dots and bars. Now under the constant force, we can modify the annuity for whole life as 1 over mu plus delta, and for the temporary life as the previous case of benefits, we will adjust it using this factor. And but for the variances, we cannot get variances easily for many cases. We have to use it, which means calculate it from the beginning. The notation is given in here, but for the whole life, this is the whole life. And for the temporary life, we have this. So we can do that replacement like these replaced with delta. We get A bar versions of these things. But to calculate these quantities, so we will have to, it's like these are the variance, so relations for the benefits. And if you need to get this, which means we have replaced, so you know that to get the, so this part is the benefit variance. And if you divide it by the D square, it is the variance of the annuity part. So these are the two equations that we can readily take out for the variance of the whole life annuity and the temporary annuity in terms of the benefit present values of those two insurers. But for the other cases, we cannot take it easily like this. So those are the things we have to keep in mind. Then we can move to the concept of calculating the premium value. So that is the final aim. And yeah, we have 10 more minutes, so I'll quickly go through some points of that. So I wanted to go these notations clearly so that you can identify these during the exam and even in your future applications. So the premium calculation depends on one type, which is the equivalence principle. So to the equivalence principle, we have to think about the loss at issue random variable, which means I have mentioned that these payment schemes and also, which means for the benefit and the premium, these payments happens in the future. So we have to discount it back to the present case, and the difference of these present values is the loss at issue. So we have a loss at the issue. But so then we need to get the so we get a premium payment from the policyholder where the expected loss at issue is equal to 0. So that is the motive of defining the premium using the equivalence principle. That means first we have to define the random variable loss at issue. So this is loss at issue, which is 0. That's how define it. So it is the present value at 0 for future benefits minus the present values of future premiums. And then under the equivalence principle, we set the expected value of this loss at issue random variable to 0. Then we can have the premium value corresponding to this scheme. So we call that premium as the net premium. Suppose I have an insurance. The benefit is $B and I am paying premium of P dots. And if it is fully discrete, then the present value is, the benefit present value is this, subtracted from the premium present value. And I can rearrange it like this. And the expectation says this. So the variance says, since this is a constant and this is a constant, so this is the random variable, and the variance of that random variable, I'll replace this. This is the present value random variable of a benefit, and for the whole life, it is given in terms of this. So it's that easy. And for the continuous case, you will replace these things by Tx and A bar. So for continuous case, replace A with A bar and D with delta. So that is the case, and you will have to adjust this double dot with bar as well. And that is how we can modify this thing. So using this, for the fully discrete case, I can define the premium in terms of the benefit that we want to pay, and the ratio between the present value of the benefit and the present value of the series of payments of annuity. So then it is same as this, or you can replace everything. So in here you have only the annuity value, and here you have only the present value of the benefit. And the variance will be p square, and this is the variance of the annuity of whole life. And for the fully continuous payments, the P is defined in terms of the B and the continuous present values of benefits and the continuous present value of the annuity payments. And it will have the same case. We will replace D by delta, and P is the benefit amount, and we will replace this with the continuous value. The variance of L naught is P square, and variance of the continuous annuity. So like in the insurance present values and the annuities, we can define for the net premiums for the whole life, the premium calculated using so in here now, we can say, so this B is the benefit amount. But if we have a standard policy which pays only $1 as the benefit, so then we can denote the premium corresponding to that benefit as PX for whole life. And we have discrete payments. So that is for whole life. And for the term life, the payments or the premium value is present value of this one and the series of payments for N years. But these are for standard policies, but someone can define so using these equations, you can define the premiums for different policies. The concept is changing the time of the benefit payments, and you can have a different payment period for the premium. So like for the 20-year term life, you can have 10 years of payments of premiums, but the coverage valid for 10 years and 20 years. So in that case, this one is 20 and this one is 10. So it is a more general case. So this is the more general case. And for the PO endowment, we have this. And so this says to get one payment at the end of N years, we have to do series of N payments worth this much amount. And finally, the endowment is the $1 endowment and $1. This is the temporary life. So this is how we define this premium for standard policies, means $1 benefit and $1 series of payments. Let's say premium payments using the standard policies. This is the amount you have to meet. So if you have a specific amount, multiply it by that amount to get the corresponding premium. And finally, we can move to the reserving part. So as I mentioned, at some point of the case, which means that in the timeline, so we will have different cases. Or before that, I'll mention like this. For an example, in this, we have a term life covered for N years. That means the benefit is paid during this time. But the payments can occur. So the premiums are paid. The premiums are paid for this time. So then easily you can define the premium as this over this. So if this is discrete payments, which means the benefit is paid at the end of the year of death. And the premium is paid at the beginning of the each year. So that is how a special case. So and also if the benefit is P, so you will multiply it by P. So that is how you can modify it. So that is the example. And finally, suppose during the timeline, we start, so in the equivalence principle, we says at this point. So at this point, the present value of future benefits and the present value of future premiums are equal. But suppose in this case, So after M years, I have paid my benefits or premiums, but the coverage goes for N years. That means during this period, the company doesn't have a cash inflow, but they are expecting outflow. That means the present value of future benefits is not equal to present value of future benefit is not equal to the present value of future premiums. So this can be extended to other parts as well because it's all equal only at the beginning. So throughout the other time period, it's not equal. Then the company should always keep some reserves to meet that benefit in future because the inflow doesn't meet, the present value of inflow doesn't meet the present value of the future payment. So that amount is called the reserving part. So do that like the calculation we did for the loss at issue. So now we can have the net premium policy value, which is a random variable at time t. What is the expected loss? So then the present value at time t of future benefits and the present value of future premiums at time t is taken, and the difference is the loss. So this is a positive case. The random variable is positive. And using the prospective method, we can calculate the reserve that we want as the expected value of this future difference of the present values. So the present values of future inflow and outflow, the difference of these two present values. Inflow, so this is the outflow, this is the inflow. So difference is positive and we get the expectation, and that is the expected present value of future benefits minus the expected present value of future premiums, and this is called the net reserve we need to keep at time t. So at time 0, at t equals 0, the future time is 0 because we know that if we are calculating the premium using the equivalence principle, this is 0. And also, if it is N-year insurance, term lives, so then at the end, it is 0. And if the insurance is N-year endowment, then this is equal to the endowment payment because it is paid at the time of t equal n. In term life, we don't have a payment at n, so that is why it is 0. And here, the expected value is 0 at time t equals 0 because the premium is taken using the equivalence principle. So those are the 3 things that you need to keep in mind. And finally, we can write down this in special formulas. If we have a B amount of benefit payment So then I can write down the policy value or the expectation of the policy value using two different annuity payments and the amount of benefit, or using the benefit present values and the amount of benefit. So those are the things that we have. And so that is the end of the summary. And yeah, so there's one more thing. So if I draw this, so I said all the benefits are considered and a series of premiums are considered to get the net premium. So if you incorporate expenses, then all these three will give gross premium. So what you have to do is just define the present values and get the expected present value for expenses and incorporate it to do. So expenses is also a kind of outflow. So that means you have to get the present value of benefits and the expenses minus the present value of premium to calculate the gross premium. The net premium is we neglect the expenses. That's why we had the present value of benefits minus the present value of premiums. So those are the concepts we used. So that is how we can wrap up the topics we discuss. And yeah, I'll share this document with you and you can have your own notes as well. But I conducted this summary session because I wanted you to familiar with the notation, and I think most of the doubts related to the notation is cleared. And since you have the equation sheet, so you know what are the equations included in that, and so you can use some of these, which means so you have to use some of these benefit actual present value of the benefit schemes and actual present values of the payment schemes like annuities, and then using those to calculate the premiums using the equivalence principle. And also you need you have the ability to calculate the reserve for a given time using the expectation of the net premium policy values, which is defined using the difference between the future benefits present value and the future premium present values. So if you get the expectation of the net premium policy value, you have the reserve that you need to keep at that time to meet the future benefits. So that is the whole story that we were discussing throughout this lecture series. And yeah, so I think this is enough to meet the which means requirement, the course, and also I have designed the final exam in with three questions, and those questions will cover some of these selected parts from this content. So there will be no extra contents considered in the exam. And yeah, so if you need to be familiar with these equations, and if it's hard, you can email back to me or requesting a cheat sheet if it is possible. So I can allow you to bring a cheat sheet to the exam. So it will be kind of an open book, but you are only allowed to get a handwritten equation sheet with use, and I have to check it with the department if they are okay with that. So I can accommodate that with you, but you have to request it, and then I will check it with the department whether I can give you permission. So which means I can conduct the exam as a open book. But I think even in the past years, it was a closed book because we are providing the equation sheet and the table. So you can go through the table and the examples I have provided in the lecture notes and also the assignment questions. The exam will be something similar to, so the exam question types will be similar. We will have a similar form as the examples we have discussed and the assignment questions that we have discussed. So we can stop the lecture right now, and I'll stop sharing and